Right. Okay.
So good afternoon, everyone. Thank you for joining us today on our short talk about exploring alternatives to REST for accessing public data sets. We hope that by the end of our presentation, you all walk away with a better understanding of the usage, current issues, and our analyzed solution in accessing and integrating public data sets. So beginning with a short introduction, as Kevin has already mentioned, we are all second-year computer science students at the University of Waterloo. We met Kevin through the RBC Borealis AI program last year and have been continuing to work with him throughout the summer. We'd like to thank him for all of his support and guidance, as well as Rohan for this opportunity. So during today's presentation, we'll be going over a couple of introductory topics from what is public data and current accessibility challenges to potential solutions and a concrete example of this solution in action. Beginning with why public data, although the sole concept of publicly available information produced by both public institutions and private sectors may be simple to many. Many fail to actually see its uses beneath the surface. For one, public data begins with the fact that it is in itself valuable data and serves as the basis for research and analyses conducted in a variety of fields, from the social sciences to economics and healthcare. Researchers can utilize these data sets to conduct studies, such as by analyzing trends and deriving insights on various topics. More emphasis, however, is put on the first word, that being public, whether it be from legislative policies that make it mandatory for sectors to publicly share their data, to organizations whose sole purpose is to redistribute data without restrictions. The point is that everyday members of society are able to access, learn, and build upon this information. In this process, public data sets also promote transparency in the government and other organizations by making relevant information accessible to the public. This transparency fosters accountability and allows citizens to understand and inquire into government decisions through the knowledge of this data, ensuring that decision makers are held responsible.
Public data is meant to empower citizens, researchers, and policymakers with the knowledge and insights to make more informed decisions that drive innovation. For example, public data is a crucial part of policymaking. Governments often release public data sets containing information on services, demographics to the public. This enables citizens to be more informed and engage in their civic duties, as well as help policymakers use this data to inform and support decision-making processes. Public data can also drive innovation by using the research to serve as a foundation for creating new applications and services to better support the community around them. These released datasets provide valuable insights on what may be potentially lacking in the community, leading entrepreneurs to solve a growing need. A notable point to make is that public datasets facilitate collaboration, allowing researchers and organizations worldwide to unite and tackle global challenges. What public data aims to accomplish is not just simply educating, but to foster a connected, empowered, and collaborative world where everyone can use this knowledge for positive change.
Now, how do we consume public data sets? First up, we have glossy reports, which generally consist of reports prepared for stakeholders to disclose corporate information, and in more general cases, it is a report that aims to inform individuals about specific information and topics. These are usually visually appealing and research-intensive reports that transform raw data into engaging diagrams and images. They aim to communicate complex information and insights effectively to a broader audience. As an example, we have here a report from the Williams Institute in which analyses were conducted upon state criminal justice data to examine the enforcement and impact of HIV criminal laws. Next up is journalism. So public data is used to create narratives in journalism that inform, educate, and resonate with the public, as well as to increase our general global awareness. This is most likely one of the more common forms of public data that you'll see, whether it be through physical newspapers to online publishers like the New York Times. Replacing simple static pictures of graphs and plots, data dashboards offer interactive and real-time insights on various types of data. These interactive visuals can provide deeper insights through data visualizations that avoid the use of complex or confusing large data sets to sort through, thus serving as effective tools for monitoring and insights. An example is the Health System Tracker by Peterson KFF on screen.
The next example we'll be going through is counterfactuals. Counterfactuals are analytical tools used to explore alternative scenarios, providing insights for strategy planning and necessary backup plans. Their main purpose is to evaluate cause and effect. They enable users to have a deeper understanding of the potential impacts of various decisions and events. The example here we have on screen is from our very own mentor, Kevin. What he created here was a tool to show how many counties one could move around to see how Donald Trump could win the 2020 elections. All of this is based on electoral data. This tool aims to show how precarious the electoral college system is, and that only a few changes can be made that change the whole outcome of the election. The next is academic papers. Academic papers are scholarly works that leverage public data to create insightful and informative reports. While these papers themselves are public data, the focus here is that they utilize public data sets and information extensively in their analysis to tackle complex problems and reveal new insights. The academic space is an environment of innovation, dedication, and a common quest to discover new knowledge. Public data helps researchers educate and inform others about the discoveries across various disciplines. The next one we have here is online data repositories and its use with APIs. Online public data sets are a wealth of information accessible via the internet. To access these data sets, APIs, which are application programming interfaces, are required. They enable the user to interact with these data sets by facilitating the manipulation and retrieval of them. From there, they can be integrated into various tools and analyzed by the user. In Canada, one of the largest online data repositories containing public data about Canada is Statistics Canada, commonly referred to as StatCan. It collects data from censuses, surveys, and records and releases them to the public on their website. These diverse examples illustrate the numerous ways we interact and consume public data. From glossary reports to data dashboards, these formats present information in an engaging and accessible way. But a critical question comes to mind is how and where exactly can we find the raw data these polished forms utilize? Unlike the simplicity of accessing these refined data in user-friendly forms, accessing the raw data can be a very difficult process. But what good is this valuable raw data, this treasure trove of information, if it's buried under layers of difficult user interfaces and inaccessibility? As we dive deeper, let's use StatCan as a case study to explore the challenges of accessing public data.
Currently, through StatCan's website, anyone can obtain their data by navigating to their data section and searching for their desired data set through keywords such as date and other types of filters. After finding your desired data set, you can then filter data by reference date, geographical location. However, at this point, we're just viewing the data. Most people would need to download the data to do their own data explorations and personal research. To actually obtain and download the data set, you then have the option to select parts of the data set you would like to pull and then download the data as a CSV file. You also have the option of obtaining the metadata file if needed to identify different aspects of the data more closely. However, imagine a situation where someone is interested in studying several data sets. This could include downloading hundreds of data sets, if not more. This is where most commonly one would be inclined to use StatCan's web data service. StatCan offers a free REST API that users may access to request available data in custom queries, to filter data by various parameters such as date ranges, geographic locations, and specific data categories. This REST API allows the data requesters to seamlessly request and manipulate data in bulk in the programming language of their choice. This API is great for users who want to observe and analyze large amounts of StatCan's data. However, it is important to note that in order to do so, users must learn some sort of domain-specific language that StatCan employs in their web data service. For someone who is exclusively using StatCan's data, this doesn't pose much of an issue. However, now imagine that there's an individual who does not only want to obtain a Canadian census, but also a comparable American census from the US Census Bureau. On one hand, obtaining the Canadian census would look like something you see at the bottom of the screen, and obtaining the American census would look something like what you see at the top of the slide. We can see that there's a clear difference between these two examples, even if it's just simply looking at the base URL. Both StatCan and the US Census Bureau have their own unique formats for requesting data. Furthermore, we can see that StatCan data is taken as a zip file, and the US Census Bureau is not. These are just some of the differences in obtaining the data from both platforms. And it illustrates how users must learn how to obtain data from every domain because there's no standardized way of storing the data.
So as Chiara mentioned for us, the most common solution to accessing and actually building upon public data through REST APIs has various downfalls that do reduce the accessibility and purpose behind providing public data in the first place. We solely wanted to get information regarding the population of states in America or the provinces in Canada, but note how complicated this process entailed and how much more complex it would get if we undertake different filtering queries like population, income, and more. So how do we simplify this? Well, a simpler method is to take advantage of SQL. So standard query language, SQL, is a standard language used to store, retrieve, and manipulate data in databases, which accessing information contained in large data sets becomes a process as easy as select statements such as the one on screen. Now, the complicated task of selecting all entries from the table where the provinces Nova Scotia, Ontario, Quebec, and the year is greater than or equal to 2020 becomes something as simple as allowing us to restrict necessary information through these statements instantaneously. So how exactly are we doing this? What allows us to connect, access, and retrieve information like the indicated line on screen?
A solution to this would require a standardized format for representing and efficiently exchanging data between programming languages and systems. Our main goal with this is to have data be shared and exchanged efficiently without the need for complex data transformations that may lessen efficiency and increase error potential. We want to be able to optimize both memory and processing efficiency and possibly reduce overhead costs in the process. Something like this is crucial in computing environments where various components of a system are written in different languages. Cross-language data standards ensure that data can be moved between platforms and operating systems without issues. A standardized data format ensures that we can reproduce the way we access data over many platforms and consistently and accurately recreate or reproduce data. We can reuse these methods across various projects to efficiently employ the same data for various purposes. We can also scale and obtain and query data to larger databases. We can then conveniently maintain and update our data preprocessing methods in a reliable condition and allow for many users to speak the same language and help facilitate data sharing, integration, and communication among various stakeholders.
Well, one example of such standardized data formats are Parquet files, of which can be connected through various libraries such as Apache Arrow. Following the main point of standardizing data formats, this process exposes the backend endpoints holding the standardized data format, which allows for various tools to be used in different endpoints as long as the backing format is the same. For example, StatCan can expose census data, whereas the Department of Commerce can expose trade data, in which the same tools such as Power BI can easily connect both in the background using SQL. Additionally, the use of Parquet offers many advantages from providing consistency in data access to reducing costly data serialization and deserialization. This building process becomes simplified for users, allowing them to develop alternative frontends without needing to host and organize this data. Hence, this process reduces development efforts as well as maintains uniformity and simplifies data retrieval interactions. Building off of this, the main point is to recognize how easily transferable and adaptable the setup serves. Integrating with different tools that are more popular in the data science community, like DuckDB or Polars, allows for a more accessible and smooth operation with softwares and libraries that you may already be familiar with, and hence reduces the learning curve trade-off mentioned earlier.
Parquet has a columnar format, which is optimized for efficient data compression and encoding, making it ideal for storing large datasets. Now, with a standardized file format, all we need now is a tool to read, write, and manipulate datasets and operate between different systems. A tool that works on Parquet is DuckDB, a database management system that harnesses the benefits of Arrow. The Arrow library provides a unified in-memory data format and a plethora of computational tools for diverse ecosystems. One can think of DuckDB as a compiler in this analogy, capable of translating these complex Arrow functions and placing them on a user-friendly interface. While Arrow is versatile and can be used with various tools, our focus here today is on DuckDB due to its capability in SQL operations and its use of Parquet, which inherited from Arrow, thus enhancing data manipulation, storage, and analysis. Arrow integrated into DuckDB forms a powerful combination, especially when paired with Parquet's columnar format. This union enables for efficient data storage, agile data querying, and uniform results across all platforms. Large organizations such as StatCan may benefit from this streamlined approach of using tools like DuckDB and storing their data in a Parquet format, as they not only offer scalability and interoperability, but also seamless integration into existing data pipelines, thus enhancing overall data management efficiency. By focusing on clearer data presentation and storage, and simplifying data retrieval methods, we can make these technologies more accessible to a wider audience, ensuring that public data not only remains public, but also user-friendly and easily retrievable. Going back to our initial problem of how do we form that connection and get caught, now we have it. DuckDB and its data handling of Parquet files. We can see above that DuckDB establishes the connection through duckdb.connect. From there, we set up a few details such as our endpoints, access key, and a few other basic information. Once you obtain this, at the bottom, we use call.execute, stating the file we want to download and any filters we want to query by, and then we are done. Connection established and data downloaded. Another notable advantage of DuckDB is in conjunction with online cloud storage applications like Cloudflare's R2, which is a cost-effective alternative to S3 storage. A key advantage here is estimated reduction in infrastructure costs, as DuckDB is well suited with S3 interfaces, thus offering a substantially cheaper alternative to compute interfaces. While saving on infrastructure, there is that possibility of a trade-off of increased network transfer costs. This arises from the need for the data to still be transferred over the network to and from the cloud storage, which may result in increased costs associated with data transfer and bandwidth. Although there is this possibility, we hypothesize that users typically fall into three categories. These three groups have their own distinct data download patterns, and we researched how they might benefit from a Parquet and DuckDB infrastructure. The first group of users are those who want to download data in bulk. For these users, our network savings are negligible as they incur the full cost of downloading everything all at once. The second group of users are those who choose to download datasets based on a few specific filters. This is where the beauty of Parquet shines. Parquet allows us to structure and orient our files for efficient querying and a few standard filters through a process called predicate pushdown. This method skips irrelevant data sections aided by hard partitioning, which acts like breadcrumbs, aiding the process. The execution of these few standard filters becomes very cheap to then execute. We hypothesize that most users will want to query by a range, such as a range of dates or a range of years. Common filters like these are well supported, making data retrieval more network efficient. However, the effectiveness of this approach still requires thorough testing. The third group of users are those interested in downloading only a select columns or select examples. They benefit from Parquet's columnar format, which enables more efficient data processing and querying. This potentially reduces the need for high-powered computing resources, but this still requires further validation on our tests. Overall, while Parquet and DuckDB's infrastructure provide significant benefits, especially through Parquet's columnar format and predicate pushdown, further research is required to validate our assumptions.
Going back to the previous example showcasing how to download data from StatCan, let's dive into some of the issues we see with StatCan's current data format and how we would resolve those issues by utilizing a standardized data format such as Parquet. As mentioned before, StatCan typically outputs their data in a CSV format. However, there are some issues with using this format. Before jumping into why Parquet is a better solution, let's look into why CSV is not ideal for this purpose. For instance, CSV stores data row by row, which has proven to be significantly less efficient for reading and processing large data sets, where you only want to read specific columns of a data set. CSV requires reading entire rows, even if some of the data is irrelevant to the query. CSV also lacks built-in support for schema evolution. In fact, StatCan does not provide much data or information about the type of data stored in their data sets. In CSV, data types are often implied, which can lead to data type conversion issues, which we saw in some of StatCan's data. This forced us to make more complex adjustments to the parser to accommodate the lack of uniform structure. Additionally, sometimes the CSVs would not parse if some value contained a double quote character, which would eventually break the parser. StatCan currently also offers a separate metadata file, CSV file, which makes it more difficult to work with simply because there's more data files to work with. In CSV, null values are also often represented as empty strings, which is the case for StatCan's data and can lead to data ambiguity. And lastly, oftentimes CSVs are stored in a larger format, which is harder to compress. In the case of StatCan, they provide zip files that do become smaller and they do compress data. However, it takes a longer time to process and open those zip files. In contrast, a Parquet format or a Parquet file is a columnar storage format, which is highly efficient for analytical workloads. It stores data in columns rather than rows, allowing for better compression and faster query performance under the assumption that people are interested in pulling columns of data versus entire rows. As mentioned, Parquet files are typically compressed, which reduces storage space and enhances I/O performance. For example, one file that was zipped to 6.5 gigabytes expanded to 120 gigabytes as a CSV, but the Parquet converted version was only 7 gigabytes. When comparing the time to unzip the CSV and opening the Parquet file, working with the Parquet file processed much faster. Parquet files also support a schema evolution, which means that you can add, remove, and modify columns in Parquet files without breaking compatibility with existing data. Parquet enforces a strict schema, ensuring that data adheres to a predefined structure to avoid the aforementioned issues seen with CSVs. Parquets also have a built-in metadata information, making them self-descriptive and easier to understand. Parquet also has built-in support for null values, providing a clear representation for missing or optional data. And because Parquet stores data in columns, it can skip over columns that are not needed for a particular query, leading to significant performance gains. It thus supports predicate pushdown, which means that queries can skip entire blocks of data that do not meet a certain criteria.
Okay, so continuing with this now converted data through optimal Parquet file conversions, the next step is to consider optimization of these large data sets. As we're pulling a multitude of different data sets over decades of years in our StatCan example, one of the strategies for optimization was to convert this data to Hive-partitioned Parquet data sets. In essence, Hive partitioning is a partitioning strategy that is used to split a dataset's tables into multiple files based on a specific partition key and organize these files into folders, allowing for more efficient query response time and storage. In our specific case for the StatCan project, we utilized Hive partitioning by year in our Parquet datasets, which also favorably worked well with DuckDB. This decision to partition by year was following the concept of predicate pushdown techniques, in which the most common filter in data analysis usually follows by filtering by year.
Now, on to where we decided to store our data sets. We have chosen Cloudflare's R2 for our data storage. R2 is Cloudflare's S3 alternative, with its notable feature of zero egress costs, which is the cost one incurs for moving our data out of the cloud storage. This aspect is extremely beneficial considering our anticipation of frequent exports of our data, thus allowing us to keep our costs at a minimum. Now, moving on to the next stage for our project. Our next stage involves conducting thorough testing. For example, we are looking to stress test and evaluate the efficiency of our R2's data storage in Parquet format, as well as test our hypothesis of whether common filters actually increase network costs. Now that our data has been stored via Parquet and is now accessible via SQL statements, we believe that these data sets and the code to obtain them are not only more visually appealing, but more accessible as well. Our next step is working with community members, like you all in the audience today, to derive good benchmarks and determine the overall feasibility of our project. As such, we invite you all to join us in this journey. We are seeking partners to help us continue testing, build more use cases, and refine our approach. So for those in the audience today who actively work with StatCan data and other online data repositories, please reach out to us through the email here and to help us improve our process. We are firm believers of continuous self-improvement, and this reflects in our continuous efforts to elevate our project to new heights.
Okay, so in our journey of navigating complex data interfaces to the much more simple, streamlined approach, we have seen many improvements. Tools like DuckDB, supported by Arrow infrastructure for manipulating Parquet files via SQL, have been vital in simplifying data interactions. This is evident in the transition from what we initially had to our refined approach. Our aim in advocating for these tools stems from our passion to enhance the accessibility of public data sets. We believe public data sets should not only be public, but also easily accessible and readily usable. As such, we'd like to continue learning, exploring, and making strides towards our goal, with this just being the first step in our long line of findings and improvements. To conclude, we'd like to thank you all for joining us, and we welcome any questions you may have. Thank you.
Thanks, everyone.